Okay. So looking at the exercises you were left with last time, just want to have a look at one of these and then we'll move on and look at the next step, which is this one, d2y by dt squared plus 2dy dt plus y equals 0. That's the one, okay? d2y by dt squared plus 2dy dt plus y equals 0. First step, write down the auxiliary equation, which would be, Daniel, what would be the auxiliary equation for this one? M squared.
Plus 2m.
Yeah. Right, equals 0. Look at that. Do you remember we were talking this morning, or this early session this afternoon, and also last week about trying to recognize certain forms? Anybody recognize that? It's a perfect square because? Yeah, half the middle value, which is 2 to get 1, and 1 squared is 1. So this is an example of a perfect square. So I can jump straight to this. I can rewrite that left-hand side as a perfect square, Daniel. Okay, you could go through, as we've discussed, the quadratic formula, but you end up with the same solution. And it's obviously much quicker if you recognize it. So what do I do from now? Well, that's the quadratic formula. Yes, yes. So what I do now at this point to solve this is square root both sides. So m plus 1 equals 0. And so what does m equal? Minus 1. So we've got one root roots are real and the same. So k equals minus 1, and the solution has the form. In this case, we're looking at y with respect to t. So we've got y equals a plus bt e to the minus kt. That's the form of the solution. If you look at your table of solutions, you see that written there. I've just used y and t instead of y and x, which is in the table. K is minus 1. A plus bt e to the minus t. Right, Daniel? Yep. In the solution, if we look at this, where does the t come from? If we're looking at this, t. Yes. Of course, we could put the t or the x in the general solution with the x, with the a rather than the b. So we could rewrite this as a x plus b e to the minus t. A and b are constants, so it doesn't matter which constant we put the x with. Actually, it shouldn't be an x, it should be a t, shouldn't it? So the t could go with either constant. So the general solution could be written like that or like that. Of course, to get the solution in the textbook, all they've then done is expanded out the bracket. So you could just as easily write this as a t e to the minus t plus b e to the minus t, which is as it's written in the exercise. Okay, so have a go at the rest of those questions in there and just check you're happy with that. That's finding the general solution for a homogeneous ordinary differential equation. And remember, this forms the complementary function for the inhomogeneous ordinary differential equation, which we're coming to.
Solve it using the perfect square, or just how we have been doing it.
So, next thing I want to do is to look at finding the values of these constants, a and b, in this complementary function, or the general solution to the homogeneous form, by putting in these boundary or initial conditions. And if you look at this particular question on here, it says, determine the general solution of this quadratic equation. It's a ordinary differential equation. Homogeneous because the right-hand side is 0, so it's exactly what we've been doing. And then find a particular solution, which is what they mean by finding the constants a and b, given some initial conditions. Look, when x equals 0, y equals 4, and dy by dx equals 9. So that's what to have a look at now. Right, so if we have a look at this, let's have a look at this problem then. The first step is find a general solution, which is what we've just been doing. So that's the first thing you're going to have to do in a minute. Then, when we've got to that point, we can then start thinking about putting in these initial conditions to find the values of a and b. In any exam that you do, what I'll do probably is say, here's a differential equation, show that the general solution is. And so then if you don't do that, at least you could then look at that solution and try and find the values of a and b given the initial conditions. So I'll give you the opportunity to have a go at one part and then the next part and so on. Okay? So let's have a go at this. The first thing I want you to do is to write down this differential equation, write down the auxiliary equation, and calculate the values for m, and then write down the solution. So I'll just pause this and let you do that. So the auxiliary equation is 2m squared plus 5m minus 3 equals 0. Solving that, we get m equals
minus
3 or 0.5. Okay, so we've got two real distinct solutions. So the solution has the form y equals a e to the k1x plus b e to the k2x. So we can write the general solution y equals a e to the minus 3x plus b e to the 0.5x. And again, it doesn't matter whether or not you write a e to the, which one goes where, okay? And that's the complementary function, or the general solution to the homogeneous form. Now, that we need to go to what we're interested in this part of the session, which is how to find these values of these constants a and b. We've got two constants to find, a and b. A and b, okay? So we need two equations to set up so we can find them. We need to set up two simultaneous equations to find these two unknowns. If in a later example we had a third order differential equation, that would mean we'd have three constants to find, so we'd need three equations. Now we need two equations. So we need two sets of initial conditions, and if you look back at the question, you can see when x equals 0, we've got two pieces of information. When x equals 0, y equals 4, and the differential equals 9. So that allows us to set up our two equations to solve simultaneously. And that's what we're going to try and do now. So let's have a look. We've got that y equals ae to the minus 3x plus be to the 0.5x. So we look at the first set of conditions. X equals 0. When x equals 0, y equals 4. So we can write x equals 0, y equals 4. That's our first set of conditions. When x equals 0, y equals 4. So we can write 4, because y equals 4, equals e to the minus 3 times 0 is just 0, plus b e to the 0. So that's our first equation. Anything to the power 0 is 1. So we can therefore write that 4 equals a plus b. And that would be the first of our two simultaneous equations. We've got two unknowns, a and b. We need another equation to try and find them. So we use the other set of initial conditions. When x equals 0, the differential equals 9, I think it was, wasn't it? Yeah, the differential equals 9. So we've got to take our general solution, y equals a e to the minus 3x plus b e to the 0.5x, and differentiate it to get dy by dx. So what we do is we differentiate this general solution to get dy by dx equals, and then substitute 9 for that differential when x equals 0. So what do we do to differentiate this? When we differentiate an exponential function, the number comes down, doesn't it? It goes in front, so that will become minus 3a e to the minus 3x, the power stays the same, plus 0.5b e to the 0.5x. We've now got an equation for the differential, dy by dx equals this. So I now let x equals 0. I should have said when x equals 0 here, dy by dx equals 9. So that means I can say 9 equals minus 3a e to the 0 plus 0.5b e to the 0. Again, anything to the power 0 is 1, so e to the 0 is just 1. So we've got that, yeah, minus 3a plus 0.5b, and that forms the second of our two differential equations. So let's just put them together. We've got equation 1, which was 4 equals a plus b. So 4 equals a plus b was the first of our two simultaneous equations. So now, well, there's a couple of ways that you can solve simultaneous equations. One is by elimination, making a or b the same, and the other is by substituting one into the other. So I could rewrite number 1 as a equals 4 minus b. And then in equation 2, instead of writing a here in this part, instead of writing a, I could write 4 minus b. And I'd have an equation that only involved b, which I could solve to get b. So that's one way I could do it. However, in this particular case, it's probably easier just to do elimination, because if I take equation 1 and half it, yes, I will get, so divide equation 1 by 2. I get 4 divided by 2 is 2. equals 0.5a, if you like, or a over 2, plus 0.5b. And we could call that equation 3. So now I've made b the same in equations 2 and 3. So how do I eliminate? Take one away from the other to get rid of the 0.5. If we look at it, if I do 0.5 minus 3a, that will give me a positive answer. So I'll probably end up doing 3 minus 2. Will give me the easiest one to deal with, although either way would work. So equation 3, take away equation 2, will give me 0.5 minus 3a is plus 3a, so that will give me 3.5a equals 2, equation 3, take away equation 2, 2 minus 9 is minus 7. Dividing both sides by 3.5, a equals minus 2. Now what we do is substitute a back into one of the original formulas, either 1 or 2, doesn't matter. 1 is the easiest one to use, so let's use 1. So substitute back into 1. Our value for a back into 1. So 4 equals a plus b. A is minus 2. So b equals 6. So we've now got the values of our constants, a and b. Oops, was I? So, finally, before we put our values for a and b back in, a good point Keith makes, you could put your values of a and b back into the other equation, equation 2 in this case, to check you get 9, and you know then you've got the right values for a and b. So finally, the particular solution to the differential equation, or the ordinary, the ODE, the ordinary differential equation, which was, what was the first equation? D2, 2, 5 and minus 3. So 2 plus 5 minus 3 equals 0 is, so a was, now we have got to make sure we put the right constant with the right value, Daniel, haven't we? Okay, so a was minus 2, so if we look at our general solution, it's minus 2 e to the minus 3x y equals minus 2 e to the minus 3x plus, what was the other one? 3. What was b? 6. 6 e to the 0.5x. And that would be the particular solution. So have a go at this one. Find the general solution by forming the auxiliary equation and solving it. And once you've got the general solution, put in the initial conditions that when t equals 0, x equals 3, and dx by dt equals 6, and find the constants a and b. Okay, so the auxiliary equation will be 9m squared. Oops, nope, I'm on a completely different page. Go back. Yeah. The auxiliary equation, 4m squared plus 2m minus 6 equals 0, which leads to m equals, what was it again? What was these? 1 and minus 1.5, leading to the general solution. What we're using is our variables here, x and t. So x equals a e to the t plus b e to the minus 1.5 t. Now we need to put in our initial conditions, so have a go to find the values of a and b. Okay, so putting in the first initial condition, when t equals 0, x equals 3, we can write 3 equals a e to the 0 plus b e to the 0. So therefore our first equation is 3 equals a plus b. And that would be our first simultaneous equation. And we have to differentiate. So if x equals 0.ae to the t, dx by dt will equal just 1, because there's a 1 in front of the t, so 1a is just a e to the t minus 1.5 b e to the minus 1.5 t. And then we put in our second set of initial conditions, which are that t equals 0, dy by d, or dx by dt equals, what was it? 3. So I can now put those values into there. 3 equals a e to the 0 minus 1.5 b e to the 0. So our second simultaneous equation is 3 equals a minus 1.5 b. And that would be our second simultaneous equation. Now all we have to do is solve those simultaneous equations. Yeah, made a mistake here. So dx by dt in this case equals 6, not 3. So actually this should be 6 equals. Sorry about that. So I would recommend for this you do 2 take away 1, equation 2, take away equation 1. It doesn't really matter which way you do it, just trying to make life easy for yourself. 6 take away 3 is 3. A take away a is 0, so the a's have disappeared, which is what we want. And minus 1.5b minus b is minus 2.5 b. So now we divide both sides by minus 2.5. b equals 3 divided by minus 2.5, which is, what is it? 6, yeah. Six divided by 5. Sorry, 1.2 minus 1.2. So b equals minus 1.2, and now we can put that back into one of the original equations to find a. So substitute in equation 1 is probably the easiest. 3 equals a plus b, and b equals minus 1.2. So 3 equals a minus 1.2. So a equals 4.2. So we've got a equals 4.2 and b equals minus 1.2. And we can put them back now into our general solution, which was there. So x equals A, which is 4.2, e to the t, minus 1.2 e to the minus 1.5 t. And that would be the solution to the differential equation, the particular solution. Let's look at another example. Problem number 2, so I'll just let you make a note of that. Yeah, so what's the auxiliary equation? 9, oh, it's on freeze. 9 m squared minus 24m plus 16 equals 0. This turns out to be a perfect square solution, or the solutions are equal and real, and it turns out that m equals minus 4/3 or 1.3 recurring.
Okay, so if you do it perfect square way, you get an answer. If you do it in a normal thing, I don't get
That's the solution. So that means we have that in this case the general solution is y equals, and again you can write the x with the a or the b, ax plus b e to the minus 1.3 recurring x. That's the general solution. T, yeah, sorry, yeah, we're using t in here as the independent variable, aren't we? T. Yeah. Yeah, that should be a minus. Yeah. So now we've got to find our values for a and b, and we're given some initial conditions again, so the procedure is the same, but obviously it's a slightly different general solution. So the first step, t equals 0, y equals 3, and the differential equals 3. So first of all, y equals 3 when t equals 0. So putting that into the original equation, we get y equals a times 0 plus b e to the minus 1.3 times 0. So in other words, y equals b. And y equals 3, so 3 equals b. So b equals 3. So much quicker this way. Okay, so immediately we know what b is. So now all we have to do is to differentiate that function, and then we can find a. So what's the original function? Y equals at plus b e to the minus 1.3 recurring t. We need to differentiate this. Now, I'm going to leave you with this, and we'll start this next time. I'll just start you off with it and remind you of what is involved. I've got a function here, and I've got to differentiate with respect to t. And if you look at it, t occurs twice. So I've got two functions. So I need to use the product rule. Okay? Use the product rule. Look back and remind yourself what the product rule is. Let the bracket at plus b equal u and e to the minus 1.3 t v. Remember the idea of the product rule, let one part equal u, the other part equal v. Use the product rule to find the differential, and then you put in the initial condition that when t equals 0, the differential equals 3. So have a go at it, see if you can get out the answer, and we'll start with that next week. Okay, so just a quick recap before we finish. Let's go back to the beginning of this section. So last time and at the start of today we talked about finding that complementary function, the first part, the general solution for the homogeneous form, in other words, when the right-hand side equals 0, which ends up just solving a quadratic equation. So we've had some practice at that. Then we need to think about putting some boundary conditions in. And because we end up with two constants in the general solution here, for example, at e to the minus t plus b e to the minus t, we need two situations to find it. And here they are. When x equals 0, y equals 4, and when x equals 0, the differential equals 9. Two sets of conditions so we can find the two constants. We've had a look at some examples where we've done that. It often involves finding the two simultaneous equations and then solving to find the values of a and b. Okay. Next week we'll finish off that example. What you might want to do in the meantime is to just carry on with those questions on page 40 of Helm as well. Okay. All right. We'll stop there.